Howdy, y'all. Let's talk about momentum. Now that we've discussed energy, we can finally talk about what is the second most important idea in all of physics, the conservation of momentum. Just like energy, when we say momentum is conserved, that means that we can't make any on our own. It has to be given from something else, which seems reasonable. You know the law of inertia, an object can't just start moving on its own. Well, the momentum is how this happens. Now, the further you go into physics, the more important energy and momentum become. These are some of the foundations that everything else is built upon. So these really are the fundamental ideas that the universe operates under. So pay attention to these. They're really, really important. Now, in the simplest form, momentum is just P equals mv. Now, for units, for lots of other things in physics, when we have combinations of units, we give it a special name. Like we had a kilogram meter per second squared, and that was a force, we called it a Newton. Or we had a kilogram meter squared per second squared, that's an energy, we call it a joule. Well, here I get a kilogram meter per second, and we call it a kilogram meter per second. You know, if you want to call it after me, that would be just fine, but nobody's going to know what you're talking about. Now, one interesting thing, if you do some unit algebra, you can prove that this is equivalent to a Newton second, just like how a joule is a Newton meter. And that's actually going to be a helpful way to think about things. The most important thing in this equation, though, is to remember that momentum is a vector. It points in the same way as velocity, which makes sense. If my velocity is going to the right, the momentum goes to the right. But remember, when you add these together, we're going to talk about vectors, not scalars like energy was. Newton actually wrote his laws in terms of momentum. So he didn't write down F equals ma. What he wrote down was force equals delta p over delta t. Now, if I remember that acceleration is velocity divided by time, these two equations are algebraically and logically equivalent. But remember inertia. You've got an object that's moving and its velocity can't change on its own. That's Newton's first law. And now I can say an object's momentum can't change until a force acts on it. And we can define force as a change momentum over change in time. This gives us a really helpful equation. To be able to change a momentum, solve this for delta p, and I get that's force times a time. So if I want to change your momentum, all I need is a little bit of force and a little bit of time. So to compare and contrast this with the energy from last time, we define this concept called kinetic energy, 1/2 mv squared. It's changed by work, which is a force times a distance, with a little cosine theta thrown in there. And we had this work energy theorem. Work is a change in kinetic energy. Or in the long form, I can say Fs equals 1/2 mv squared final minus 1/2 mv squared initial. Same kind of idea now, but with momentum. We define this new thing, momentum, P equals mv. It's changed by an impulse. This is the force times delta time. So I get this theorem, impulse J equals change in momentum, delta P. Now you will sometimes see other letters for impulse, but capital J is one of the more common ones. But I'll normally just call it an impulse instead of a J. And so if I plug it in, I got my long form. Force times time equals momentum final minus momentum initial. This is a really helpful way for talking about single objects and how force changes momentum. Now, just like conservation of energy, a system can't get momentum on its own. So I want to now think about systems instead of individual objects. For conservation of energy, we really only talked about single objects. But for momentum, we want to talk about systems. Now, I can define energy as a system by adding up the energies of all the objects in my system. That can be great sometimes. For momentum, what I'm going to do is talk about, say, two objects, and the momentum before something happened and the momentum after something happens has to be equal because momentum is conserved. No matter what happens to the objects, even if the objects smash into each other or one blows up into a million bits, if I add up the momentum of all the bits, it would be the same as the momentum was before the explosion. It's a really powerful tool. Now, the mathematical proof just comes from Newton's third law. When two objects collide, the forces are equal and opposite. And so I can prove that a momentum in one object is the opposite of the momentum change in a second object. And now we can finally do the physics of collisions. So remember, every momentum problem, you write down initial momentum equals final momentum. Write down the P equals mv for everything in the system before and after, set them equal to each other, and solve. It's just that straightforward. So one simple example to get us going. So here I've got two ice skaters. We've got the person in purple and the man in the green shirt. I'm noticing a decided lack of sequins from what I normally see in figure skating. But anyway, they start at rest. They push off against each other. So I have this 54 kilogram woman and an 88 kilogram man. The woman moves off to the right with a speed of plus 2.5. Now Newton's third law says if he pushes her, she pushes him back. So he goes off to the left. Let's find out how fast he goes. I'd really encourage you to pause the video here, solve the problem on your own, and then see what happened. Alright, now obviously we solved this by conservation of momentum, because this is the video on conservation of momentum. So if the initial momentum is 0, because her initial is 0, his initial is 0, so the momentum of the guy plus girl system is 0 plus 0, which is 0. So the final momentum here must also be 0. Okay, so mathematically, I say P final equals P initial. And I write down, okay, my initial momentum is 0. And for my final momentum, I'm just going to do the mv's for all my object. So I got m1 v1 for the girl plus m2 v2 for the guy. Now remember, momentum is vectors, so these velocities are like vectors. They have signs. They can be positive or negative. It's not speed, it's velocity. Now in my problem, I was given m1 and m2. I was asked to solve for the guy's final velocity, so I'll solve my equation for v final 2. All right. This minus sign says that my velocities are going to be pointing in different directions. And these masses are going to tell me if my guy is faster if he was lighter than the girl, or slower if he is heavier than the girl. Now I know he is heavier, so his velocity should be a little bit slower. That can be my good reality check to see if I got this right. Okay, plug in the numbers. I've got the mass of velocities. Don't forget that minus sign. Negative 1.5 meter per second. Because he was heavier than the girl, he's going to be going a little bit slower. And because she went right, he went left. So that's it. Write down P initial equals P final. Write down the MVs for everything in your problem. Solve, and you are done. Now, one thing physics students often get wrong is they say they believe in conservation of momentum, but they don't actually believe in conservation of momentum. So there's a famous thought experiment that says, what happened if everyone on Earth got to the same place and jumped simultaneously? Well, the answer is not much, but we can prove what happens. Remember that momentum is always, always, always conserved. It's one of the deepest principles of physics. So if I jump up, not only is the Earth pushing me up, but I am pushing the Earth down. Because if I get an upwards momentum, the Earth must get an equal and opposite downwards momentum. It has to happen that way. Now, the math is the same as the ice skater's problem. So I can say, well, if I can jump with a hang time of about a second, which is a little generous, my initial velocity must be about plus 5 meters per second. My mass is about 80 kilograms. So I've got 5 times 80, so that's 400 kilogram meters per second of upward momentum. So I give the Earth negative 400 meters per second of momentum. That's momentum in the downward direction. Now the Earth is a smidge heavier than I am, 6 times 10 to the 24th kilograms. So when I solve with the same equation as last time, I get its final velocity is a little slow-ish. So at this speed, 10 to the minus 23 meters per second, it takes about 10 years to cross a proton. Now, even if all 7 billion people on Earth did this at the same time, the velocity is so small you could never, ever, ever see it. Now, if you want to have some fun, go read what happens after the fact on this XKCD what-if scenario. Just remember that even when the objects are disproportional in size, they still conserve momentum. All right, one last idea, and then we will call this a day. When things collide, and we're always going to do momentum for collision problems, we have two ways that we can think about these that will give us some simple cases to help us solve problems. One type of collision is called an elastic collision. And in this case, I drop a ball, it bounces back up to its original height. So that ball bouncing off the floor was an elastic collision. In that case, the total kinetic energy is the same before and after. Now, if it's not perfectly elastic, then it's somehow inelastic. The total kinetic energy is different. Now, energy is always conserved. What that means is some of the energy from the ball went into making sound or heat, some other form of energy. So when it bounced, it was going a little bit slower. Now, if it was completely inelastic, they get stuck together after the collision. So if my ball doesn't bounce at all, it just goes poof and sits on the ground. That's the sound of completely inelastic. Momentum and energy is always conserved, but the kinetic energy in the equation depends on the situation. Let's take a look at a simulation to get a feel for how momentum works. So this is from the PHET, P-H-E-T. Just Google that and open up the collision lab. It takes you to this. So I've got two objects, the red one and the green one, and they're going to collide. This green one starts at rest, red one's moving to the right. I can turn on momentum vectors, and the velocity vector is green, the momentum vector is yellow. So if I change the velocity, the momentum changes to follow it. But if I change the mass of object 1, its momentum also changes. More momentum for heavy stuff, less momentum for light stuff. Now let's reset this, and I'm going to click on More Data. So I see the momentum and velocity. So for object 1, its momentum, its mv, is 0.5 times 1, which is 0.5. And for object 2, its initial momentum is 0. I'm going to turn the speed down a little bit. Let's watch these guys collide. Object number 1 comes, it hits object number 2. And notice what happened. After the collision, its momentum is negative 0.25, and the green one's is positive 0.75, but the momentum of the system, this plus this, is 0.5, just what I started with. If I reset everything, let's now change the elasticity. So I'm going to drop this down to about half. So let's check our data here. I still have the same initial momentum of my system is going to be 0.5. Let's do a collision, and let's stop. Now, I have less velocity afterwards than I did with a perfectly elastic collision. These objects are traveling slower. However, momentum is still conserved. My red one has negative 0.06, my green one is at positive 0.56, and the difference between these is still 0.5. My initial momentum equals my final momentum. So now if I go all the way down, I make it completely inelastic, and we hit play, they get stuck together. They travel with the same final velocity, and if I were to add these momenta up, 0.13 plus 0.38 is going to round off to 0.5. Momentum always conserved. So we can use this to find an equation for something that's going to be helpful for us in these momentum problems. If and only if I have a perfectly elastic collision, and if and only if one object was initially at rest, I can calculate the two velocities with the simple equation. Now there's two unknowns. So I've got object 1 with initial velocity, collides object 2 at rest. I want to know the final velocity of object 1 and the final velocity of object 2. Well, two unknowns needs two equations. And my equations are conservation of energy and conservation of momentum. So the kinetic energies add up because I have a completely elastic collision. So my kinetic energy before is my kinetic energy after. My momentum is conserved, so the mv for object 1. Remember, object 2 is at rest, so I left out the mv here for the initial momentum. Equals the final momentum, m1v1, m2v2. By the way, I'm calling the initial speed of object 1 v0, just to make life a little bit easier. All right, I get two equations. I got to solve for two unknowns, v1 and v2. And it's a little bit of work. You actually have to bust out the quadratic formula. It takes a fair amount of algebra, so I'll do it for you. And when we do that, we get some simple equations. v1 equals v0 times this term about masses, and v2 equals v0 times this product of masses. Now remember, they only work for completely elastic collisions. We're also assuming that object 2 is at rest. Now, I could bend that rule a little bit by thinking about moving to another frame of reference where that object is at rest, but we won't worry about those details in these basic lectures. All right, so when I have the situation, feel free to use these equations to find the final velocities. I wouldn't suggest doing this algebra on your own unless you just enjoy a little extra math. So for elastic versus inelastic, remember we've got the initial bounce. Perfectly elastic ball comes back to its original height. The perfectly inelastic ball goes and gets stuck, doesn't bounce at all. What about the variations in between? Well, I want you all to see there is a commonly defined variable, normally a lowercase e or an epsilon. This is called the coefficient of restitution. I wanted you to have heard about this before we called it a day for momentum. This little number is a number between 1 and 0, just defines how bouncy was it. 1 for perfectly elastic, 0 for perfectly inelastic, and some other number for something else in between. Now this is the fraction of relative speed after the collision. So if my ball was coming down at 10 meters per second, but it bounced up at only 5 meters per second, my E would be 5 divided by 10, or 0.5. Just a nice measure of how elastic the collision is. I wanted you all to see what coefficient of restitution looked like, to visualize the difference between elastic and inelastic and everything in between. So here's a little demo I wrote in the processing computer language using the Box 2D physics engine. So I've got some objects here. The numbers and the color is based on their coefficient of restitution. So this bright red one on the left is a 1.0 perfectly elastic ball. The one here on the right is a 0.0 perfectly inelastic ball. And here's everything in between. So as they bounce after their initial height, momentum is always conserved. However, the ones that are not perfectly elastic, they're going to lose some speed after they bounce because momentum is being transferred, well, into the wall. So when they bounce, they'll go up a little bit slower, and you'll see that this green line here matches the height of the initial bounce. Let's let them go and see what happens. All right, now they started here at this blue line at the top, and we see that the more bouncy ones with the higher coefficients are still going, and this guy here should be coming up exactly to the top and coming back down, but life is hard and this engine isn't perfect, so it's actually getting a little bit of extra velocity there. So we can keep going, we can play around and add some more, so let's click and let's add a couple more things. So there's another ball. We can get these to bounce and roll. Now the size is proportional to their mass. So if it's really big, it's really heavy and going to really bust something as it goes. This is a lot of fun to just kind of play with and get a feel for how objects bounce. If you enjoy coding and you enjoy playing with this, really encourage the processing language and the Box 2D physics engine. I've made a lot of really fun things with it. I will try to get a copy of this code up on GitHub if you all want to play with it sometime later. All right, in summary, whenever two things collide, you have a conservation of momentum problem. Always use conservation of momentum in that situation. Write down initial equals final, write down the MVs for all the objects before and after the collision, do the algebra and solve it. The momentum of the system is the same before and after. Now I have been saying collision, but keep in mind here they don't actually have to touch. They could be interacting in any way with, say, a magnetic force or an electric force or a gravitational force, but no matter how they interact with each other, the momentum of the system can't change. Now, if there's some kind of external force, well, then our system's just not big enough. When you're solving these problems, also look out for keywords like completely elastic. Then I can use those two equations we wrote down earlier, or completely inelastic, which means things are stuck together. All right, you are all set to solve any problem now with collisions and the conservation of momentum. Thanks for watching.